This video we're going to prove a very interesting fact. S sub n, which is their permutation on a set of n numbers, it has a normal subgroup of index 2. It's called the alternating group, and it's denoted by an, and it consists of all the even permutations on this set S sub n. Proof is pretty slick, I think. It's a standard proof. So we're going to define W to be the group that just contains 1 and negative 1. Contains the real numbers 1 and negative 1. 1 and negative 1. And this is under multiplication. Good exercise for you would be to prove that this is actually a group. It only has 2 elements, and it's multiplication, so nothing's very hard there. Now we're going to define a mapping. We're going to define phi that goes from S sub n to this set W by phi of S. S is in Sn. It is a permutation on their n numbers and objects. And it is going to be 1 or negative 1. And it's going to be 1 if S has an even number of permutations, and it's going to be negative 1 if S has an odd number of permutations. Now, the first thing I want to show is that phi is a homomorphism. Is phi a homomorphism? Okay, so let S1 and S2 be in Sn, where S1 and S2 are both even. So psi of S1, S2, even times even is even. So this is 1, but 1 is 1 times 1, and that 1 is phi of S1, or it can be thought of as that. And that one we're going to think of as phi of S2. So when S1 and S2 are both even, we get the results that we want. Okay, now let S1 and S2 be in Sn, where both are odd. Be in Sn, where S1 and S2 are both odd, and in both cases I should say permutations, odd permutations. So phi of S1, S2 in odd times an odd is an odd. Okay, I was a little bit sloppy in something. Over here, we have multiplication. Over here, we're going to think as an addition. If you add 2 even permutations, you get an even permutation, which is 1. Now, if you add 2 odds, you get an even. So this is 1. But 1 is the same as negative 1 times negative 1. And that negative 1 is phi of S1, because S1 is odd, times phi of S2, which is also odd, hence negative 1. Phi of S2 is negative 1. Okay, so it worked when they're both odd. Now, let S1 and S2 be in Sn such that S1 is odd and S2 is even. So phi of S1, S2, well, an odd plus an even is odd. Well, that's negative 1. Phi of an odd number is negative 1. But negative 1 is the same as negative 1 times 1. And this here is the same as phi of S1, because S1 is odd, phi of S1 is negative 1. And since S2 is even, this 1 is the same as phi of S2. Now, I won't bother showing it, but if S1 is now even and S2 is odd, you're going to get the same result. Phi of S1, S2 will be phi of S1 times phi of S2. So, putting this all together implies that psi is a homomorphism. Well, what's the kernel? What is the kernel of phi? Let's call that K for kernel. Okay, what is the kernel? Well, S is in K if and only if phi of S is the identity in W, which is 1. But the only way you get 1 is by definition, if S is even. Okay, so S is in K if and only if S is even. And we gave a name for this set. Okay, consisting of all even permutations. It's denoted by A sub n. Just wanted you to see it. So, K is just A sub n. Okay, now let us see what we have. We have phi, which is a mapping from Sn to W, where the kernel is A sub n. That means this mod, the kernel, is isomorphic to W. So we have this. And let's see. The kernel, which is An, is normal in S sub n. Okay, so now let us look at something else. 2 is equal to the order of W, but that's the order of, based on this, that's the order of Sn mod An, but that's the order of Sn over the order of An. And starting from right here, anything I write is extra. So what I wanted to show was that S sub n has a normal subgroup of index 2. And what I showed is that this subgroup is of index, I showed that that subgroup is of index 2. Okay, so now what I want to continue here, this is like bonus. This is equal to the order of Sn over the order of An, but the order of Sn is n factorial. The number of permutation on n objects, distinct objects, is n factorial divided by the order of A sub n. Well, 2 is equal to this. 2 is equal to this. And it's common knowledge, or at least it should be common knowledge, that you can switch those. These are real numbers. This implies that the order of An is n factorial over 2, which is half n factorial. So Sn, the order of Sn is n factorial, and the order of the even permutations is half of An. Well, that would imply that the order of the odd permutations will be the other half of n factorial. And that completes this video with some extras, or completes the proof. If, the letter's just formally stated. Okay, so A sub n is normal in S sub n. That's the normal subgroup. And the index of An in Sn is 2. And that's what we wanted to show. If you like watching videos like this, seriously consider subscribing to my channel. Please leave a comment. Tell your friends and family about my channel. Be nice to your enemies. Maybe not tell them about it. But go ahead, tell them. Or see you guys in the next video. Thanks for you watching to the very end. Never forget, watch and learn.